Okay, thank you so much. The title of my talk is Dark Matter and Electroweak Phase Transition. Please, next slide. And my talk is according to light dark matter, according to this paper, light dark matter around 100 GeV from the inert doublet model. Please. I'm going to talk about the beyond standard model. Thank you. And scalar electroweak multiple dark matter, the IDM model, the simple but very useful model for dark matter, the IDM global fits, and finally the conclusion. Okay. A standard model cannot describe all phenomena in the nature. For example, gravity. For gravity force and neutrino oscillation and neutrino mass, matter antimatter asymmetry, why there are more matter than antimatter, and what is the dark matter. And a standard model cannot describe this phenomenon. And I try to focus on dark matter. Okay. And there are some evidence for dark matter. For example, CMB shows that dark matter must be 5 times of ordinary matter. And in the bullet cluster, when two clusters collide each other with gravitational lensing, we see that most of matter are in blue region, not in the purple region. And Vera Rubin and Philip Zucchi in different years, according to the speed of galaxy rotation, they got it that there must be an extra matter. And these are some evidence for dark matter. Okay. And there are some candidates for dark matter: prime ordinary black holes, axion, non-interacting or sterile neutrino, and WIMP, weakly interacting massive particle. And in this talk, I focus on the WIMP. Okay. I want to introduce a general form of the potential, a scalar electroweak multiplied dark matter. Okay. And in this case, we use the most general and renormalizable scalar potential. We, according to this, into this reference, we add a doublet. It can be doublet and or multiple. In our case, it is doublet. We add in the electroweak representation a doublet with a iso spin and hypercharge to the standard model, and we try, according to reference, we try to write a maximally complete form for potential. Okay. It is the usual inert doublet model. People usually use this model, H as a Higgs doublet and Q as an extra doublet that people add to the standard model. There are lambda 1, lambda 2, 3, 4, lambda 5 as a parameter of this model. It's a usual form of the IDM. And we try to find the general form and maximally complete form for the IDM. Okay. In this slide, we see that the general form of the IDM, we have Higgs as a doublet and an extra doublet Q we add to the standard model with the transformation matrix in the SU2 representation. H bar as a transform matrix for Higgs and Q bar as a transform matrix for a extra doublet. we can compare the coefficient and the parameter lambda 1, lambda 2, 3, 4, 5 in the usual doublet in the right hand side, and in the left side you can see lambda h, lambda 1, alpha, beta, kappa 1 as a parameters in the general form of IDM. We have some coefficient, sorry. Okay,
sorry. Yep.
Okay, no problem. In equation 6, you see some coefficients. These coefficients comes from the Kelebsch-Gordon coefficients. In the equation 3, we have Q with half isospin and QQ with one isospin, and finally we need a sentence with we need a term with zero isospin because our potential is a scalar. And according to this paper, we write this potential. Okay. Next slide, please. Thank you. And after electroweak symmetry breaking, we see the mass of the of our fields. We have a scalar field, equation 7, pseudo-scalar field, equation 8, and equation 9 as a charged field. We consider MAS as the lightest particle and as a candidate for dark matter. And so we need to have this constraint less than 0, and this relation must be satisfied. Okay. In this table, we see the vertex factors for the IDM couplings. We can see the self interactions and interactions between dark matter, candidate of dark matter, and Higgs. And lambda is as a triple and quartic couplings between the standard model Higgs and the dark matter candidate. Okay. We use some constraint on the IDM, on the general form of the inert doublet model. Vacuum stability, the potential must be bounded from below, and perturbative, our coupling must be limited. Oblique parameters show the the difference of our beyond standard model and standard model, limits from colliders, and first order electroweak phase transition. And I want to focus on the first order electroweak phase transition. Okay. And what is the strong first order phase transition? We can see in the standard model, the electroweak phase transition is crossover. It means that order parameters change smoothly and continuously. Okay, you can see in the in this figure, you can see what is the crossover. The order parameter change smoothly. When the universe was hot, everything, we are in the symmetric phase. When the universe are cold, we have a phase transition. And this phase transition is first order phase transition. It means we have some bubbles like boiling water. We have some bubbles. Phase in the bubbles is completely different from phase outside of the bubble. The order parameters here is the vacuum expectation value of Higgs. In the symmetric phase, we have 0 vacuum expectation value. And in the bubbles, we see that we have the wave as a 246 J. Okay. When we have some bubbles, we have a Spaileron rate. A Spaileron rate describes the rate of baryon number generation and washout in the first order phase transition. We have a graph that this graph shows shows that in the first order phase transition, we have to generate minimum in the origin, and when the temperature is equal to the critical temperature. Okay. And but sorry, wait.
Okay.
And okay. And in the strong first order phase transition, the Spaileron rate must be less than expansion rate. And in this case, we have the strong first order phase transition, phi SC over TSC greater than 1. Okay. In the global, the IDM global fits. Okay. We have a general form before I want to say a summary. We have a general form of the potential. We say maximally complete form of potential. We have some constraint, vacuum stability, oblique parameters, collider search, first order phase transition, and we have a model as a potential and some constraint, and we want to use the global fits for this model. In our model, the parameters, we have a physical mass of the IDM, MS, MR, MI, and lambda as a coupling between dark matter and Higgs. And we have D as a MH as a Higgs mass, omega H as a relic density, VSC by TSC as a constraint for first order phase transition, and other constraints from vacuum stability, collider search, oblique parameters. In equation 12, we have the likelihood of the IDM parameters, OI corresponding to the corresponding to the our parameters. It's a function of theta, a function of our parameters, and mu I and sigma I comes from the experimental. Okay. Result from the global fit. What is happening for dark matter when the first order phase transition is not strong? It means VSC by TSC is between 0 and 1. Okay. In this plot, we have a one-dimensional posterior plot for IDM. In the right-hand side, you see that VSC over TSC is between 0 and 1. And in the left side, we see the mass of the our fields in our models. We see a flat, thank you. We see a flat graph between 2000 around 4000 in our case. When VSC by TSC is between 0 and 1, it is a one-dimensional posterior distribution. And when we consider VSC by TSC between 0 and 1, we see a flat shape for the mass of our models. Okay. And what happens for dark matter when we have a strong first order phase transition? It means VSC over TSC greater than 1. Okay. In the right hand side of this figure, we see VSC over TSC is greater than 1. And the effect of VSC TSC greater than 1 we see in the left hand side in the mass of the our fields. We see that we have 100 GeV peak for the dark matter. So when we consider a strong first order phase transition, we can find light dark matter around 100 GeV from the inert doublet model. And it was a short result from our papers. Okay. And it's finished. Thank you so much.
Okay. Thank you, Leila.
Okay.
I'm not sure if you hear the applause. It sometimes gets swallowed in Zoom, but it's recording here. Yeah. So are there, unfortunately, we are kind of late at the moment, but is there a quick question from the audience? Maybe, so I have a question. So you talked about the fit. Can you say briefly, what is the data you are fitting to?
Sorry, what is the data?
What is the data that you are fitting to? Yeah, in your global fits.
Okay. We use some package for our data. For VSC by TSC, we use beyond a standard model BSMPT package. And for our potential, we use LandHev and micromegas. We add the Lagrangian in the LandHev and use output of LandHev in the micromegas. And by micromegas, we have some results, some data for relic density. You can go to the page on the for the global fit page. Sorry. In the global fit page. No, global fit page. Okay.
The global, yeah, I don't see the global fit page. Okay, but I will have a look at the. I will have a look at the slides. I guess fortunately, I don't.
We use some package, and according this package, we have our data. Okay. You can.
Okay.
For VSC by TSC, we use a BSMPT package. For the relic density, we use the micromegas package, and we have this package for our data.
Okay, let's have another round of applause for Leila. Thank you very much.
Thank you.